Okay, good morning. Good morning. This is Professor David J. Delosreyes. My topic for this morning will be it's actually March 15, 2023. The time is around 3:19 a.m. Okay, my topic for this morning will be Advanced Mathematics, and this is lesson number 20. So again, I will be deriving, I think this will be formula number 6. Formula number 6 for the Laplace transformation for circuit analysis. Okay, let's proceed. I will check my camera. Okay, the topic for this morning will be Advanced Mathematics, lesson number 20. This is Laplace transform formula number 6. This is formula number 6. Formula number 6 is actually this one. For this. Okay. I will try to read the final formula before I will give the so-called derivation. The Laplace transform of any differential function of t will be equal to capital letter S function of s minus f sub 0 plus, where f sub 0 plus is actually the value of function of t at time t equal to 0. We will subtract the initial value of the condition at time t equal to 0 for us to take the Laplace transform of any differential function of t. Okay, I will try to repeat it. The Laplace transform of any differential function of t will be equal to s function of s minus f sub 0 plus, where f sub 0 plus is actually the value of function of t at time t equal to 0. Okay, let's proceed with the derivation. The derivation is just simple but needs a complete thinking on how we were able to derive the so-called formula. Okay, let's bring out the derivation. For tonight, the transformation formula is actually the Laplace transform. This is a symbol for Laplace of any differential function of t, and this should be equal to, if we are trying to bring out the general equation on how to take the Laplace transform of any function, it will be equal to the integral from 0 to infinity of the given function times e raised to minus st times differential time. Okay, let's substitute the value. The Laplace transform of differential function of t, this should be equal to the integral from 0 to infinity. Okay, I will try to remove first this one. The given left hand side is actually the differential of any function of t, okay, times e raised to minus st times dt. Okay, then as a next step, this is differential, okay, it's not derivative, because differential is just d and derivative is actually d over dt, something like that. So I will transfer the location of this one. I will place it here. Okay, so I just rearrange this one. So the right hand side, after the so-called rearranging, it will be the integral from 0 to infinity of the derivative with respect to time of that given function of t times e raised to minus st. So actually this dt here is not anymore here, we place it here. Okay? To solve the integral of the right hand side, I think it falls under the so-called integration by parts, that is actually ub minus the integral of b du. Okay, let's proceed with the solution. If the solution of the right hand side falls under the so-called integration by parts, we will assume a value of u and we will assume the value of dv. And in here, we will assume that the value of u is actually e raised to negative st. This portion here, we place this as u. and what remains will be dB. Because actually, this is the integral of b du under integration by parts. That is, the integral of b du will be ub minus the integral of b du. Okay? So we must have to specify the value of u and b, then we will try to integrate the integral of b du to integrate the integral of b du. Okay. If u will be e raised to negative st, du will be, s here is constant, right? It is constant. So the differential of u, we are taking differential, not derivative. It will be e raised to minus st times the derivative of the exponent. And the exponent is actually a constant times the variable t. So it will be negative s times 1. So the total derivative of the exponent will be negative s. So the coefficient of du now, I place it here. Okay, I expedite a little bit. It will be negative s e raised to negative st times dt. Okay, and what will be dt? What will be dB? dB will be, if this is u, and this will be dB. So therefore dB will be the derivative with respect to time of function of t. But what is the derivative with respect to time of function of t? That is actually f prime of t, right? So integrating both sides, the integral of the differential of b will just be simply b. When the integral sign goes near this differential trine, they will try to cancel out each other. So what remains on the left will just be simply b. And for the right hand side, okay, it will be the integral of f prime of t. And what will be the integral of f prime of t? It will be just be simply function of t. Okay? So b in terms of t will be b as a function of t. I will change my camera. Oh, it's still fine. Okay, let's proceed. So we now know the value of u and we now know the value of b. So following this equation here, we will just substitute, right? The value of u is actually e raised to minus st. And the value of b is a function of t. So I just rearrange it. It will be function of t times e raised to minus st. This is actually with the limit from 0 to infinity. Okay? This is minus, so this is minus. Okay? The integral from 0 to infinity of b du. What is b? B is function of t. And what is du? du is actually minus se raised to minus st times differential time. It is this. Okay? So what will come out? I will just copy this one. It will be function of t e raised to minus st with the limit from 0 to infinity. This is minus s. So this will now be plus. Since s is constant, we bring it out. So this will now be s. The integral from 0 to infinity of function of t e raised to minus st times dt. Then, if we try to recall the formula on how to take the Laplace transform of any given function, it is actually this, right? The integral from 0 to infinity of any given function of t e raised to minus st times dt is just the capital letter f as a function of s. Okay? Okay, this is infinity. Okay, let's try to substitute now the upper and lower limit for the first one. So it will be function of t, okay, times, if t here will be infinity, what will come out will be e raised to minus infinity, and this should be 1 over e to the infinity, or this should be 1 over a big number, And 1 over a very, very big number will just almost approximately is equal to 0. So when we place time t to be infinity, the upper limit is 0. Okay? Same as the last time around. Okay, I will erase this one so it looks nice. Okay, let's apply the lower limit. When time t is 0, minus s times 0 will be 0, and e to the 0 will be 1, so this is minus 1. Why this is minus? We are subtracting the value of the given first term, okay, upper limit, lower limit, so there's an operation subtraction over here. So this is minus 1. Plus s as a function of s. Because this one here is the simplification of s function of s. Or this portion is function of capital letter f as a function of s. Okay? So I will try to rearrange now. I will write first this one. So s capital letter f as a function of s minus. Why this is minus? This is minus, right? So this is minus f sub 0. Okay. Sorry for this one. It will just be simply f sub 0 plus. Okay. This designation here is the value, the initial condition. The value of the function of t initially at time t equal to 0. That's the meaning of this. So in Laplace transform, if you see a function, a quantity 0 plus, the meaning of that is the value of the function at time t equal to 0. That's the meaning of this. We will subtract the initial value at any time t equal to 0. Or it's just like in the so-called RL circuit. At time t equal to 0, what will be the current? So the meaning of this, at time t equals 0, what will be the current? That's the meaning of this. If we are talking of current, okay? So I will repeat it for the last time. The meaning of this is f sub 0 plus is actually initially at time t equal to 0. What will be the value of the function? That's the meaning of that. Okay, I will try to erase this one. So that's it. So formula number 6 now. The Laplace transform of differential of function of t will be s function of s minus f sub 0 plus, where f sub 0 plus is the value of function of t at time t equal to 0. Okay? We neglect already the time t at equal to infinity because the value is actually 0. But at time t equal to 0, okay, the value is not 0. There should be a value. But at time t equal to infinity, because this is negative, okay? At time t equal to negative infinity, the value of e to the negative infinity is almost approximately 0. But at time t equal to 0, the value e raised to 0 is actually 1. And we designate that as simply f sub 0 plus. Okay, I will repeat it for the last time for this morning. The Laplace transform of differential of function of t will be s function of s minus f sub 0 plus. Oh, that's Laplace transform, right? We are converting function of t to a function of s. Then we will use algebraic manipulation. We will take the inverse Laplace again to take the final solution. So for tonight, for this morning, the Laplace transform of any differential function of t will be s function of s minus f sub 0 plus. And f sub 0 plus is the value of the function at time t equal to 0. Okay, that's it, guys. I will check my camera again. That's it. So for those students or friends of ours who are taking advanced mathematics, this is for you guys, okay? So if you want to subscribe to my long-form video channel, okay, my channel is actually at youtube.com/@ProfDavidJDelosReyes, and if you want to share it, please click share. Good morning from Los Angeles.